So as I was saying that there was this point where changing from SIM to Google Meet handled the and several other services, and their bank data fed in by connection provided by the SIM. The SIM one was not working properly, so I wanted SIM 2. When that, what do you think happened with this all at the time in when you see SIM 1 would be off the net, step so all services with net is unavailable. Okay, so that means basically they have to take the necessary action. Means, for example, if they're sending some data, etc., they must stop because net is no more has been created. Where do about it, they would actually either they would reach out to me have any net connection, obviously, but it does not go off. But in some cases, they'll just go blank or the net connection, but the symbol stay on, not crash. Now the is Google Meet, it'll have to because the nets are not available. We put SIM 2 net on. Okay, and SIM 2 net on network basically, so no more this net, so it was connected with this. Now it's connected to, this is the SIM 2 net. So SIM 2, the subscriber identification module, that is being used as a connection manager to get onto the services that the internet services that are being provided by the network provider, whether it's Jio, whether it's Airtel, whatever it is. And so when it is on again and when a connection is established, okay, then there is another thing, all services note that net is again available. I don't part here. Well, Geo from Realme doesn't care. Care about is the net or not. So net is available. So the next is that you resume online actions. So and actions that because isn't available, some that were put, those would be once again be turned on. I'll give you another example. So what was that we interrupted the services. Basically, interrupted the services. That as a matter of saying that this is true, obviously we are um, interrupting this, and it means stopping in between. So this is interruption of services. But when I say in the service, that else it means we interrupt signals to stop the services. Make this slightly more with another So when okay the antivirus kicks in, what do you think will happen to the various other services? Well, it depends. Now, this is obviously extremely high priority because nothing can compare to this in priority, because it has to take care of the health of the computer. It has to do with the health of the computer. And the virus that puts at risk all data in this computer and all the computers and network that it can find from there. Okay. So what what does that actually mean? Look at the potential of it. That it affects one computer first, but from there, whatever computer and network that it can find, it will affect it. So how can you tell what is the effect of a virus attack? No one can tell. At best, it is 2 3 days of annoying or annoyance. And worse, your company may totally lose all its data so that it will be forced to shut down. Neither is acceptable. Anything in between is also not acceptable. That is why it is extremely high priority. And so, okay, because before the other programs may go on with, what happens is that they are all notified. Okay, all the programs are notified that okay, there has been a virus attack, and you must stop all sorts of. You must save all the data as fast as you can, or you must stop all memory access, etc. Just install it basically. Whatever. No one knows which computer program the virus has affected. So we interrupt the regular jobs that are regular. By regular jobs, I mean jobs that are going on, that are just normal jobs submitted by the operating system, including your programs and stuff. Those regular jobs are going on. You're chatting on social media, for example. Those are going on. Then it's stopped and it's checked for viruses. Now, obviously, we see these days that in the background also the antivirus can run. Uh, there used to be a time when we used to have to stall everything. Now, when the this you know when I say that the regular jobs are immediately interrupted, and I didn't say halted. Okay, so note this point that I didn't say halted. Halting means stopping all the jobs. Now they may not be totally stopped. No, it may not be the case that they're totally stopped. In fact, sorry. Yeah, that's right. But we don't need to do that anymore. In modern computers, we don't need to halt them, but we need to interrupt them. So why we do not need to halt them is because they've got several security features built into them. For example, if they are accessing some important part of memory, we don't want them to do that while the virus is there, because uh, that will affect the that important part of memory as well. Now, also, if it's just input outputting, maybe it will be allowed because it is going to a particular device and not being used anymore. But maybe if we feel that even the printer may get epic, obviously the printer has a computer inside it and some workable memory. If we believe that the printer will get affected, no matter how temporary this affecting may be, then we will not also then we will not also do the printing. So basically, that means that any job that cannot be done in the event of a virus attack will be stopped, and for that, all the processes that are on, they must be notified that look, don't do this job because there is a virus on board. and you all need to be disinfected if you have been affected. So this is done by the issuing of interrupts. So this interrupted means interrupts. Okay. So that means that this actually means send an interrupt signal to the processor to indicate that is the process in question needs to be serviced. When that need arises, and in this case, basically the antivirus, for example, interrupts, that means issues interrupt signals to the processor. Now, obviously, it might be that in modern architectures, it might be that interrupt signals are not only sent to the processor, it will be definitely, but it may also be that the interrupt signals are sent to the other processes as well in some form or the other. But for the time being, just for brevities, that is, brevity means simplicity. So, for brevity's sake, we'll consider that the processor is interrupted only and the others are not. So, how does it work? Now, let us say that this is our processor. Control unit, ALU, registers. And these registers are the accumulator plus other registers, including the program status word, stack pointer, the instruction registers, so on, and all the other registers and data registers. Every register is there. So these are the registers. Now there is this is main memory. Let's just draw the basics out first. This is data, address, and then these are control signals. Okay. All sorts of different control signals out and in are there, etc. Now we have, as usual, it is a stored program concept. So um, the stored program concept, as in, if you remember, the concepts followed from Conrad Zuse. Now let us say that this is program 1, this is program 2, this is program 3, and so on and so forth. The net connection is on. Now some bad program, let's say the virus that we talked about, has come around and affected P2. Now Just because we live in these times, I've made this virus look like a coronavirus. Obviously, you know that this looks like a coronavirus. Okay. Now, we don't want to mention the name of the virus too much. We superstitious about it, but just to keep it real. So let us say our P2 is being affected by the virus. Now, how does the virus affect it? Let's just first see that. The computer will go through P1, then P2, then P3, then maybe P4, etc. As you know, as you already have known. Once it goes into P2, alongside the normal lines of code, the viral lines of codes are also there. The virus has overwritten a part of it by itself. Immediately when this happens, the computer unwittingly will start executing lines from here and then execute the virus also. What will the virus do? The virus may do lots of different things, from annoying things like calling you names, etc. Like, for example, you're writing something, suddenly Microsoft Word comes up and says, for example, you are a monkey. Like that, it shows on screen. That is very annoying. But every time you want to do something, some screen comes up and says you're a donkey, okay, you're an ass, etc., etc. So there was, for example, when I was a very young student, there used to be a program called Melissa 2814, something like that. It is a virus that used to do this kind of stuff. Whenever you wanted to do something, some Microsoft Word window would used to come up, and it used to throw abuses at you, verbal abuses at you. Okay, and very bad abuses, in fact. So it's very, very annoying. It happens in front of your teachers or in front of your fellow students, okay, your friends, your classmates, and you can't do any work. So it's very annoying. And obviously, as I said, that can be far worse. For example, stealing someone's financial data from his own computer or something like that. That it can be far worse, actually. Now, we have to stop this from being executed. So this antivirus, so at some point of time, you see, all along this way, this memory is there, it's going on. At some point of time, we have also loaded, or the operating system by default, the way it works, it has also loaded the antivirus software. And what does these antivirus do? P1, P2, P3 antivirus. Then maybe some other processes are also there, maybe P5, P6, etc. Then suddenly, when it comes to the antivirus, it checks the entire computer. It checks the entire computer. So it checks all the processes for the virus. We call them virus definitions. Okay. Why are they called virus definitions? Because the signature of the virus, that this is the code, this is the pattern of the code, that is called the signature. So that signature is there, and the virus database has to be kept updated. So it has got a list of the signatures of the viruses that is known to it, and some other important data from which it can extrapolate one process from a virus. So all of this is done by the um, antivirus. Okay, so a valid question Diva has asked is that how does the computer know it's an antivirus? Well, actually, the computer means that antivirus actually finds out. As I said, that it matches the bit patterns with the bit patterns of virus. If the bit patterns match, then obviously that is the signature of a virus. If it matches, then it knows that a certain process has been affected. So it wants to deal with it in various different ways. For example, yeah. All viruses have specific patterns. All viruses, all viruses have specific pattern. Just like any biology has a specific DNA code. Similarly, obviously, all viruses have a specific DNA code. Because you see the DNA, because you see the virus is doing some work, some malicious work. So because it is doing some malicious work, its binary contains a certain sequence of this thing, the certain sequence of code. Now, because all viruses do stuff differently or do different kinds of stuff, then obviously their binaries are going to be different, and their binaries will help us from distinguishing one virus from another. Now, this binary, so this signature, how to detect a particular type of virus and what to do with it, all these things are kept in the viral virus database. And so that is exactly why the antivirus software needs to keep its virus database up to date. Yeah, in that case, you are very unlucky. That is true. If there is an antivirus, if the antivirus does not know what pattern it is, okay, then it is obviously true that we can't help it. Yes, yes. Every virus is got a different purpose. I mean, okay. I mean, there may be you may write one virus that does the same thing as my virus. That's a different story. But generally, viruses they're written in different types of code and different types of patterns and using different types of styles. So uh, you can distinguish from one virus from another. And the other thing is that if two viruses do the same thing, their bits patterns are going to be the same because they're running on the same machine. So just imagine that you're running it on the same machine. Because you're running it on the same machine, and if you're doing the same thing, then obviously it logically follows that your bit patterns are going to be the same. So if it's virus 1 and virus 2, and you're looking for the bit patterns of virus 1, but you get virus 2 which does the same thing as virus 1, then obviously the bit patterns are going to be the same on your machine because you're talking about just one machine. One you're talking about viruses being run on one, more particularly one machine architecture. So the same machine architecture. That's why. So just one sec. Anyway, so coming back to it, so obviously that means that the bit patterns are going to be. There is another intelligent way of is that when your virus is looking at the process, okay, these processes they have also patterns. That means it just means the pattern of bits basically. Now process one, process two, and are coming from different programs. So obviously they're and if even they do the same thing, they got a certain bit pattern. That what the antivirus might do is it might actually look up the bit patterns of P1, P2, and P3 one again and again and again and see if the patterns have changed. Now, if the patterns have changed legally, that's something. If the patterns have changed illegally, there are ways of telling it. Then there are lots of checks that can be done that would tell you whether the patterns have been changed legally or illegally. By illegally, I mean not by program control on your computer itself, by authorized access and so on and so forth, but by some unauthorized access, the bit patterns have abruptly been changed. That might also indicate that it is a virus. Because let us say P2 has a bit pattern, let's say like this, say like this. Suddenly, this part, the antivirus finds, has been changed to like that. Immediately it knows that this is not the correct pattern for P2. So that means it must check whether what will it check? It will check the records. So obviously, if something is changed, then somewhere someone is maintaining some parity or something. So if it says that it is unauthorized, then this must be malicious code. So then the cleaning starts off. How does that happen? The antivirus issues an interrupt. Okay. So it issues an interrupt by sending an interrupt signal through the interrupt line. This is called issuing an interrupt. Just one moment, please. Okay. So this now we issue. So this interrupt signal is that we should. This is called issuing an interrupt. That means sending an interrupt signal. So when in previous cases when I was talking about interrupting a program or interrupting the processor, I actually meant issue an interrupt signal to the processor. That's what it means. Now, there are other ways also that this interrupt can be issued. And for example, let us say that nothing is affected here. Normal sequence. So you have three healthy processes. Let's say P1, P2, P3 are all healthy processes. P1 has now been served by the processor and now it is using the other resources. P2 is being served, P3 is being served like this. For the time being, let's say that the processor was at P1, but P1's time has finished and it's come to P2. Now this is separate scenario that we are looking at. Now, when it is servicing P2, immediately it finds that either P1 or P3 they need IO. Means they rather, let's say that we need two IO. That means we need to either input or output or both. And let us say that it is an urgent need to do that. But processor is at this point of time, it is serving P2. So then you need to grab the attention of the processor. So because of this need to do IO, it will once again issue interrupt signal, or rather in short we say issue interrupt. And how is this done? How is this issuing an interrupt, sending an interrupt signal, how is it done? Basically, this is done through dedicated interrupt lines that run into the processor. Now this processor, you can see all these control lines that are there, or control signals that are there, signals that issue certain uh, instructions or want some attention or give some signal to the control unit, that something for the control unit to handle, that those are called control signals. So all these control signals, so one of those control signals is a DMA One of those control signals is an IO. Similarly, one of those control signals is an interrupt. Just like when we did DMA or IO, we saw that the request for DMA is issued through the DMA signal, IO signal, etc. Similarly, we have the interrupt signal. If we need to interrupt, then there you go. Now, it is these interrupt lines that are used by anyone who is issuing an interrupt. It may be the processes in memory. They cannot directly issue an interrupt. They have to use an interrupt controller. And several processes may similarly, like for example, here what has happened, these two need IO. They both issued interrupts, and there is only one processor. So which interrupt is going to be handled first? So big thing. You may say, sir, first come first serve basis, fine, fine. But then what about the signal which did not come first? Will it be then lost? It will be destroyed. Somewhere you need to know that, okay, I will, P1 has issued, P3 has issued first, P1 has issued next. So after servicing P3, I must look into the interrupt of P1. Someone should, you have to have the ability, but you're only one. Only one. You cannot handle all these interrupts all at once and queue them up and remember which interrupt came when. So here we need the help of an interrupt controller. This is basically a peripheral device that works with the CPU. Your CPU asks it to handle the interrupts for it. What does it do? It just basically services the interrupts as the case may be on the basis of priority. And if it is same priority, and well, I mean, those that are not served at the moment, those interrupts are masked and um, they are masked and hidden for the time being. And when this when the current interrupt has been handled, then the next interrupt that had come in, it will be demasked and used and so on and so forth. Okay, so I'll stop here for just 2 minutes and let you think your head into it. Just excuse me. I'll be back. So now what we have done so far is that whenever a process needs attention of the computer, that is the central processing unit, it issues through the interrupt control lines, that is the interrupt lines. It issues an interrupt signal, and it may not do it itself. It may use the help of uh, an interrupt controller to issue a signal, that is an interrupt signal, which tells the processor that I know you're busy, but you also need to service me. So that the processor in its own time can store the states of the present process. And by now you know what is storing the state. It is storing the program state on stack basically. So it can store the present programs or processes state and go on to service the other program that was needing attention. Now, because there is only one, we are dealing with one processor machine. So because there is only one processor, and whatever it is, whether it's one processor or two processors or whatever, there'll always be a race condition where processors are trying to interrupt it for being serviced, and the CPU will have to handle that. Now, that is then handled by the interrupt controller, and the interrupt controller is nothing but a peripheral device, just like the DMA controller and IO controller that we saw. What it does is it handles the interrupts for the CPU so that it doesn't have to bother about dealing with the actual operations that are the ALU operations are done by the the CPU anyways. So apart from that, it does not, so that it is not taxed in dealing with the interrupts that are coming in, what and the servicing of those interrupts, or those more specifically the subroutines and the programs, etc., that needed to interrupt the processor in the first place, servicing those so that uh, this load is or does not tax the main processor. We use this interrupt controller. And what does the interrupt controller do? It queues up the interrupts, prioritizes, and helps the processor in servicing this this queue of interrupts. This is what we've done so far. Now let's see. Look at these two interrupts. This is an interrupt issuing for IO, and this is an interrupt issued for antivirus. Antivirus work, antiviral work. So there is an interrupt signal, say here also. Let's call it just int. In 8085, it is actually called an int signal. And in P1 also, we're sending out interrupt because of this. It needs IO. It needs to do some IO. So it needs to do some IO. So it needs some particular type of data. So that's why these two interrupts are there. And this has issued an interrupt. Antivirus software, it has also issued an interrupt signal on its own. It is very instinctive that this signal should get priority out of these three. What normally happens is that what normally happens is this. The processor is on a job. So other jobs will interrupt the processor, short PROC, for want of servicing. For example, IO, AV work, antivirus work. So, etc. Now, so the processor being busy with ALU work, it will be taxed with the burden of handling a process out of turn. So processor is helped by the peripheral device interrupt controller. What does the interrupt controller do? The interrupt controller cues the processor on the next interrupt to be serviced and queues up the interrupts according to priority and turn. That means first of all priority and then first come first serve and so on and so forth. If there are several interrupts being served, the processor will be serving them as it has been doing P1, P2, P3. That is in a round robin way, same way. Okay. Now let us look at the stuff where the antivirus process issues an interrupt and say process P1, so it issues an antivirus activity interrupt. This issues an IO activity interrupt. That means basically issues an interrupt for doing some IO. It is needless to mention that this gets priority because it relates to health of the processor. Now what happens here is also that interrupt is masked, right? So it's hidden for view for the timing. When current job is tackled to some stable point, then interrupt, I would say here issued interrupt, the interrupt that has been issued, then the interrupt is demasked and serviced. So for example, if you do an IO activity interrupt, first of all it will be masked. Okay. So it looks like this. Let us say that we issue the IO interrupt by using a blue line. Then this is the IO interrupt. First of all, it is masked. Okay. Processor task stable, because when it's doing some work, the process may not be in very stable. The task that is being done by the processor may not be in a stable state. So you have to reach a state where, for example, if a current operation is being done, if it is currently being done, then it is unstable, because what is the stable state? The operation is being started, and what is another stable state? The operation is finished. In between, obviously, it's unstable. So the processor task is stable and then demasked, and then it is served. However, so this means that when the interrupt comes, the processor takes its time in servicing it. It says, okay, wait, let me just do it. But do you think that the antivirus interrupt, let us do it in red line, can it wait at all? What do you think? No, it cannot. Basically, it cannot wait. It cannot wait. So now this must be issued as a non-maskable interrupt. This interrupt cannot be masked. You cannot wait until some job is over. By then, it will be too late. The virus will take control. So you cannot wait. You must service it there and there itself. So this is a non-maskable interrupt. It's a different kind of a signal. There can be several signals. Obviously, this is built in. I mean, you cannot just say it's hardware, mind you. It does not change. So all these interrupts have to be built in. So the several control lines are there, and you will see that if you send it through the control line 1, it is maskable. Control line 2, it is maskable. Control line 3 is non-maskable. So AV antivirus will use the control line 3, so that would mean that it's a non-maskable interrupt. There will be to mask it as such. You have to drop everything and go and service it. And this interrupt, which is important but not crucial, it's basically a maskable interrupt. So any interrupt that comes in can be either maskable or non-maskable. Normally, the interrupt for, for the timing, so that they're hidden from view for the timing. The processor does its job. It does not finish it because obviously there is an interrupt, so it does not finish it, but it takes a point where it is stable, and then it stores its state and then demasks the interrupt and services it. However, certain interrupts cannot wait. For example, antivirus interrupt. Antivirus, actually, when I say antivirus, I should not do it with an oblique. That means audio visual. Actually, it's AV. I'm saying antivirus. Here it means antivirus. So antivirus, or for antiviral activities, the interrupt obviously cannot wait, because if you wait for the current process to reach a stable state, then you will service it. What will happen? The virus will take over. It will be too late. And once the virus has affected your computer, it does not. It's a very whether you'll be able to disinfect it, how long or how deep will the infection go? No one can tell. As with biological infections, also we try to avoid computer infections as far as possible. obviously. So in those cases, this is issued as a non-maskable interrupt. How does it happen? Basically, say the processor is there, and let's say these are interrupt lines. I'll call them int lines. All these are interrupt lines. All these are interrupt lines. All these are interrupt lines. Let's say this is basically maskable. This is also maskable. This is also maskable, and this is non-maskable. Then in that case, P1 might use any of these lines, say for example this one, but the antivirus software will use the non-maskable line to tell the processor that it will use this signal, particular signal, to tell the processor that look, it's a non-maskable interrupt. I cannot wait, I cannot fool around. You must service me immediately. And these on the other hands. Now, whenever P1 is installed on a computer, it will be given the particular line through which it can send the interrupt. So the nature of now this is one. So by line I mean signal. Okay. So this is one thing, that if P1 is in a crucial need of something, then it'll, instead of sending a maskable interrupt signal, it'll send a non-maskable interrupt signal. Now, how do you distinguish? Now, when I say this is a logical diagram, physically it is just only one line through which the interrupt signal is coming. So how do you actually distinguish whether it's maskable or non-maskable? Once again, by the bit pattern of the interrupt signal that is generated. One signal sequence is different from another signal sequence. So there you are. If a virus has not affected and the antivirus wants some IO to do, for example, some reports to be printed or something, it will also not produce a non-maskable signal. It will produce a maskable signal using the channels that are allocated. Okay, so using, so this is a logical diagram showing that, okay, how processes on the basis of what is the priority and send a maskable or a non-maskable interrupt. Similarly, the classification can be as follows. First of all, it can be maskable, it can be non-maskable, we already know that. Then it can be a hardware interrupt, and these are normally very high priority interrupts, are generally issued as hardware interrupts. The dedicated signals issued by the hardware, and there are software interrupts. They're issued by software. That means obviously a program is a software, but when it is issuing the interrupt, whether it is doing through hardware support or software support, that hardware interrupt or software interrupt. Now then comes the question of whether an interrupt is vectored or non-vectored. Very important concept. Vectored means, see, the interrupts, these interrupts are serviced by something called, so these are serviced by ISR, interrupt service routine. Routine, as you know, is nothing but a function. Routine or subroutine, whatever, is a function. So it is basically like this, that the processor is here, and it's the main memory. All the processes are here, say P1, P2, P3, AV, etc. And alongside it, there are also ISRs, interrupt service routines, service routines 1, 2, etc. That on the event of an interrupt, these codes are to be used. So that means that, say P1 issues an interrupt, I'll call it INT, and this may be serviced by ISR2. So when this interrupt will be serviced, the control will flow to ISR2 and ISR2 will be executed, and hence this will be served. For example, P1 had an IO request. So P1 had an, say, IO request, and ISR2 services input output. So when the interrupt was issued, the processor masked it, then asked P1 what is it. Then P1 said, I want IO. So it sends an IO request. Then ISR, okay, 2, when this is demasked, it is handed over to ISR2. ISR2 is then serviced. Now in several modern computers, you may have more than one processors for serving interrupt service. Dedicated or maybe dedicated cores of processors that will service only the interrupt service routine. So that's more efficient. But in a simple computer, it'll just, once it gets into the interrupt, it'll go to ISR2 as interrupt service routine 2. And then the interrupt service routine finds out that the P1 wants to do an IO, and it services P1 on the basis of the IO that it actually requires. Its input or output, which device, how is it going to be output. All of this is handled by the ISR. Now, obviously, all this code may not be in ISR2. ISR2 in its turn may use another code, for example, a printer driver or whatever. It may use that, but it is serviced by the ISR2. And this is called the interrupt service routine, the subroutine that handles an interrupt. And there are several subroutines for doing several different things, so that whenever an interrupt comes and it is found that, say, some action needs to be taken, depending upon that action, it will be taken to that proper service routine. So in this case, it was for IO.